All right, so let's go ahead and just talk about this first one. This whole idea of what we're doing is recognizing that when we have an accumulation of change, when we have a graph that has a curve, representing that area under the curve is tricky. So it becomes important that we understand the difference between what is our input and what it is that we're measuring as an output. Okay, so each day that goes by, I've got a plant growing. So what I'm graphing here as my output is the rate of change of the graph. How high is it growing each day? I'm not graphing its height. So my output is not the height. My height is, or my output is the inches per day. So that is the rate. That is a rate. I'm graphing the derivative. So what you're looking at here is the data for our, if you want to call it the velocity graph, we talk about position, velocity, acceleration. This is my rate. So on my first day, it's not growing at all. On my first day, it's not growing at all. Or when I have it 0, okay. Then after my first day, its rate of change was 1/2 of an inch per day. So in this one day, it grew 1/2 of an inch. So that's kind of obvious. I can get that from the graph, no problem. But we need to look at what's happening and what I'm using of that rate. So here, on my third day, it's growing at a rate of 2 inches per day. That means that in between these two, its actual rate was somewhere in between that. So I go ahead and I assume that on day 2, I'm going to go ahead and use this same rule. And I want you to think about, do you think that this lines up with either a left hand or a right hand or a midpoint sum? Because the way that I calculate this after 2 days, so we'll just go ahead and say at my 3-day conversation, I know that in between here, I'm talking about 3 minus 1 times this rate of 2 inches per day. So what I wind up doing is saying 2 times 2 is 4. So there's going to be a growth here of 4 inches during that time. My total that my plant has grown is now 4.5 inches. It wasn't growing at this rate here or here, but in between these two, I don't have that data, so I'm going to go ahead and assume this. Would you call that a right hand or a left hand sum? We'll keep going. After 8 days, so what I have here is this conversation in here. So after 8 days, I'm talking about actually 5 days. And that 5 days, I'm going to go ahead and go with 5 inches per 1 day, which is going to give me 8 minus 3 is 5 times 5, another 25 inches. When I add that 25 inches to the 4.5 that it's already grown, I'm looking at a 29.5 inch tall plant. This 5 inches per day was not happening on day 3 or day 2 or day 1, but I'm going to go ahead and assume it was happening on day 7 and 6 and 5 and 4. Would you call that a right hand or a left hand sum? Am I using the upper bound or the lower bound? All right. So after 8 days, my plant is 29 and a half inches tall. So that's my answer here for B. After 1 day, it's here. Notice I still had to calculate this in between day in order to get my calculation after 8 days. Okay, so Marge, whoever Marge is, she's like, oh, I get it. Since the plant grew for 10 days at 7 inches per day, at the end, my plant is going to be 70 inches tall. And I'm saying, no, Marge, that's not how it works. Talk to your group mates about why that plant is not 70 inches tall. Go. Ideas for what we would tell Marge. If Marge is expecting her plant to be 70 inches tall, is she somebody that's going to be disappointed by the actual data? Unless she was scared about a 70-inch tall plant. Yeah. So our conversation with Marge has to be, we can break down that growth. And since I'm looking at this derivative plant, or this derivative graph, its rate of change is not constant. So for the first part of when that plant is growing, I have 0 over 0. And then this 0.5 represents this next portion of growth. And then when I look at my 2 and my 3, I'm looking at that next portion of growth. And when I'm looking here, I have that next portion of growth. So when I asked you, would you have said it was a left hand or a right hand sum? I'm hoping you would have said right hand. Because what I'm doing is I'm using this next data point as that top for that whole thing. So I'm probably even, as this goes, getting an overestimate of how that plant is growing. Because especially between this big gap here between 8 and 3, between 8 and 3 days, on my 4th day, I don't think it was growing at 5 inches a day. On my 5th day, maybe it wasn't growing 5 inches per day, but that's the size of the rectangle that I used to calculate that area. Does that make sense? Okay. Yeah, the actual plant is about 43 and a half inches tall if I continue with this pattern using the Riemann sums. Now, if I wanted to, I could calculate it again and use the left-hand sums. If I use this as my change for here, and this as my change for here, and this as my change for here. So when you're given a chart of data, when you're asked to use a left-hand or a right-hand sum, that input-output, when you're looking at whatever rate was happening, whether you're using the rate to the left or the right, imagine this chart being horizontal instead of vertical. Your accumulation of change, what you're graphing here is you're looking at your total inches. This many inches plus this many inches plus this many inches plus this many inches is going to represent how tall your final plant is. All right, take a look at number 2. A particle is moving along the x-axis at a rate modeled by r sub t and shown in the graph. Mark the area under the curve. So this is an easy one to graph, under the curve, under the curve. It's tricky when we end up with this. Where do I color with this middle section? How would you describe it to me? Right? The little pocket, the little box. We could say the space between the graph and the x-axis. So you're always talking about when we're graphing the area under the curve. And again, if we're talking about positive movement, movement to the right, negative movement, movement to the left. This was the kind of graph that we talked about with people going in and out of a museum or a movie theater, whatever our total is. So whatever is happening along this axis is our time, and whatever is happening here is our whatever we're measuring per that allocation of time. So in this case, it's centimeters, that it's moving left, right, left, right, left, right. And we could talk about, when we add these distances together, whether the particle actually moves at all. If this is my 0 point, if this is my 0 point against the axis, and if I move left and if I move right, each of those times I might end up never traveling at all, not making any progress when we talk about that. So if we have this particle moving, if my derivative is negative, that means it's decreasing, it's moving in a negative area, in a negative direction. When my derivative is positive, that means my function is increasing. When my derivative is equal to 0, that's where my direction is changing from whether I'm moving positive or negative. So I can go ahead and calculate the area under the curve. So mark the area under the curve. We did it. What does the area that I marked represent? That's the centimeters that the particle is moving right. It's the centimeters that the particle is moving left. Our right is positive movement. Left hand, whenever it's moving to the left, that's when my derivative is negative. So here, I'm moving at positive 10 centimeters per second, positive 5 centimeters per second. Here, I'm not moving at all. My rate is 0. Here, I'm moving to the left. This is where my particle turns around. That's where my maximum is going to be. So when we talk about how far is the particle from its initial starting position, when I look here, my area of my first triangle, 1/2, my base is 2, my height is 10. The area of my second area, it's a trapezoid, so either you divide it up into 2 triangles and a rectangle, or you know the area, the formula for the area of the trapezoid. Area of the trapezoid is 1/2 times your height, which in this case is -15, times the sum of the bases, which is 1, 2, 3, 4, 5, 6. Yeah.
Wouldn't we have broken up the oh yeah, sorry, never mind. You just said it, but never mind.
I did, thank you. So the area of a trapezoid is equal to 1/2 of the height times the sum of the bases. And if you're like, I totally forget that from geometry, go ahead and divide this up into 3 shapes. You can find the area of this rectangle, you can find the area of this triangle and this triangle. And it should completely match. When we talk about the area of my third space, that's 1/2 times my base, which is 2, times my height, which is 10. So I end up with positive 10 here, plus -60 here, plus positive 10 here. So my particle is 40 centimeters to the left from its initial starting position. It's going to be 40 centimeters. Whether you call it down or to the left, that negative implies that. All right, do me a favor. Talk about 1 and 2. What do you think these questions are going to look like on the quiz? What do you want to make sure that you remember before you sit down to take it? Your mark is set, go. All right, so last question. Sketch each given Riemann sum, a left-hand sum on the interval of 2 to 6 with n equal to 8. So when we talk about our interval of 6 minus -2, we're talking about an interval of 8. And because I want 8, each of those sums, each of those rectangles is 1 width tall. So what I'm going to do for each vertical segment is I'm going to draw it from the place that it starts to where it intersects the graph. When I have a left-hand sum, I want the left-hand part of my rectangle touching. So I'm going to go to where this graph hits on the left, and if I need to complete any rectangles, I will. So this rectangle and this rectangle and this rectangle, when I talk about, forgot this one.
Disclaimer.
Yeah.
If there's a question like this where we're supposed to sketch it out and we don't include the little guys, the ones that don't really get filled up that much, we will point to that.
So, and then this is not included. Answer, or ask me that one more time.
So if there's a question on the quiz where we have to sketch this out and we leave out the ones where there's at 2 and 3 and at 5 and 6, do we have to mark that out for you? Or
Yeah, so 2 touches the graph here, so he definitely counts. 5 touches the graph at 0, so there's nothing that counts on that.
Okay.
So yeah, you will lose points if you don't include those. So when you do your right hand sums and your midpoint sums, the same vertical lines. So you draw your vertical lines from where your n is to where it touches the graph. To me, for the right-hand sums, it's easier to start from the back and work my way forward. So this is where it touches the graph. Here, this is where it touches the graph. So drawing this box is your flat part. That's what you're talking about, Anthony, right? Here's the right-hand sum for 3. Here's the right-hand sum for 2. Here's the right-hand sum. Here's the right-hand sum. Here's the right-hand sum. Here's the right-hand sum. Our midpoint sum, I think, is a little bit easier. So I'm going to draw my vertical lines. And then what I'm going to do is, in between each line, I'm going to connect my boxes. Where it looks like it hits in the middle. So you're going with where the graph hits in the middle. if you end up drawing a line and you can't erase, I'm okay with you just squiggling it out. So we're not having you do calculations for these today. We just want you to be able to look at, like, which one do you think is the most accurate? Probably the midpoint. That's where I can most easily guess. Anytime my graph is increasing, my left-hand sums are an underestimate. Every time my graph is decreasing, my left-hand sums are an overestimate. You'd like to think it balances out. The opposite is true with my right-hand sums. If my graph is increasing, my right-hand sums are overestimates, and my left-hand sums are underestimates, and you'd like to think that it balances out. Any questions on calculating the sums for the graph? Are we good?